Okay, so welcome back. We were discussing vorticity dynamics, right? And we had come to this point where we had said that this is a vector identity. Now, I want to discuss a few things about vorticity dynamics, but before that, there are a couple of more things I'd like you to see. And first, what I'd like you to do, what I'd like to do is just quickly go over boundary conditions for Navier-Stokes equations. Now, Navier-Stokes equations are a set of partial differential equations. So, like differential equations, they will require boundary conditions and they will also require an initial condition. Now, the initial condition is something that you have to specify at every location, and the velocity flow field, for example, what it is at give it at time equal to 0. And then what you have to specify is also the boundary condition, which means that you have to specify certain variables at the boundaries for all instances of time. So these boundary conditions are quite important in fluid mechanics and they always must be prescribed. Because this is a differential equation, the kind of boundary conditions that you can prescribe are similar to what you can prescribe for normal partial differential equations or normal differential equations. And one is obviously called the Dirichlet type of condition. You might be familiar with this name. In this Dirichlet type of condition, your variable value is specified at the boundary. So, for example, if you are looking at the Navier-Stokes equations, the variable is the velocity field. So, ux, uy, uz, the three components of the velocity field are the variables. So, if you specify that, that becomes a Dirichlet type of condition. If you are doing a Neumann condition, then you would specify the derivatives. Okay. One example I have made for you here, by the way, I'll share this PDF for you. So this example, what I've done is I've considered a two-dimensional flow through a rectangular duct. The duct is such that this is x, this is y. The duct has two walls which are stationary. These two walls are stationary. And this is at y equal to minus h and this is equal to y equal to plus h. And the velocity component in the direction of x is called u and the velocity component in the direction of y will be called v. So in this two-dimensional flow through this rectangular duct, one of the type of boundary conditions that you can specify is the velocity of u at all x's at this wall, which is x comma y equal to plus h, and this wall, which means x equal to u comma x, y equal to minus h. So here the x component of the velocity, this is going to be 0 because this is the tangential velocity at this point and this comes from no slip. Now at this particular position, can we specify the velocity field v, which is the y component of the velocity field? So the answer turns out to be yes, and this comes from another consideration called the no penetration condition. The no penetration condition says that if the material is solid, if this is a solid boundary, then fluid cannot pass through this boundary. So there is fluid here, but there is no leak in a sense. So this wall is not leaky. So there is no fluid on this side, but there is no fluid on this side. So at this particular location, you cannot have a finite v velocity, because if you had, then the fluid is trying to penetrate through the wall, but the wall is going to prevent penetration, right? So it's a solid condition, it's a solid boundary. So this causes us to prescribe a boundary condition called where we say that v is equal to 0 at these two walls, and this is also called the no penetration condition. It's a kinematic condition, and these two are both Dirichlet type of condition. An example of the Neumann type of boundary condition comes if you take, let's say, the half of the control volume here, such that one boundary now becomes coincident with the middle of the duct, right? So your one boundary is now at y equal to 0 and another boundary is y equal to plus h. So here you cannot apply this condition, right? Because there is going to be fluid, there can be fluid flow across this. So because there is a fluid on the other side, this is not a solid wall anymore. This is just an imaginary line that you have drawn. In this case, in our particular situation, the condition is specifically drawn such that you have symmetry on both sides. So the both sides are symmetrical. So from that you can argue that del u del y at y equal to 0 is equal to 0. And that is just the symmetry boundary condition. Okay. So this is the type of boundary conditions you might require. And the solution of this is Navier-Stokes are going to be discussed more in the next part of the course by Professor Shukla. But I just wanted to give you this brief idea. And a couple of other things about Navier-Stokes equations are that this particular term, these are called the convective terms. The other term, this particular type of term, which involves the deviatoric stress, that is called the viscous or the diffusive term. Now, the Navier-Stokes equations are partial differential equations, but their solutions are not that straightforward. And the Navier-Stokes equations are complicated by the lack of an independent equation for pressure. The Navier-Stokes equations are a vector equation, which means you have three equations for u, the three components of u. But what about the pressure? That's also a variable. But you do not have an independent equation for pressure. But we know that the gradient of pressure contributes to each of the three momentum equations. So you have this fourth variable for which you do not have an independent equation. Moreover, the continuity equation does not have a very dominant variable in the incompressible flows. We have already seen that. So you can just simplify the continuity equation and put it into the Navier-Stokes there. Then what do you do? So then this mass conservation doesn't have, you're dealing with the same three variables again there. So mass conservation in such cases can become a kinematic constraint on the velocity field rather than a dynamic equation. And the solution of the Navier-Stokes, because of this kind of problems, are associated with very elaborate techniques in computational fluid mechanics, which is not obviously going to be part of this course, but this is something for you to know in general. Okay. Now we should get back to, so I'll get you this document, as I've just written that for you. Now we should get back to this vorticity, but before that there is one more thing that I think I've forgotten. I mean, usually when we discuss continuity equation, then there's one more important function called the stream function that is discussed. So let's say the continuity equation we have, I hope you all remember what it is. Continuity equation is nothing but del rho by del t plus divergence of rho u, right? Now let us take the case of, let us consider the case of (2D) steady flows. Okay. So that implies that when my continuity equation can simplify to del x of rho u x, let's say ux is the x direction component, del y is rho uy equal to 0. Okay. Now let's define a new function psi such that so we are defining deliberately a function such that del psi by del y is given as rho ux, and del psi by del x is given by minus rho uy. Okay, so I'm prescribing a function psi such that its derivatives satisfy these two. Now substitute these terms into the continuity equation here and see that psi is going to satisfy the continuity equation. Obviously, you will have to assume that the second derivatives here of psi are continuous. So there is an implicit assumption about the second derivatives. But other than that, you can easily see that psi is going to satisfy my continuity equation. Okay. Now, the reason this is called stream function is because lines of constant psi are streamlines. And I hope you remember what streamlines are. Streamlines are lines which are everywhere parallel to the flow. Okay. And I will leave this so I'll leave this as a exercise for you to give it a shot. Okay, that you have to show that the lines of constant psi are streamlines, and that gives the variable that name, stream function. Okay, good. So now we are able to come back to our original discussion, which involved vorticity dynamics and vortex tubes and vortex, the fact that there was no sinks or sinks or sources for vortices. So let's getting back to vortex dynamics. Just a second, I need to get some water. Okay, a very useful quantity in vorticity dynamics is the variable. We'll just write it as a capital tau, okay, which is a vector quantity, and this is called circulation. Okay, so we have a new variable which is a vector and it's called circulation. But how do we define it? Well, circulation is defined as, and by the way, I hope I've written this before, and I assume that you've already known what this is. This is not an equal to, this is an identity, which means that sometimes when you define it a variable in a certain way, then that becomes the identity equation. Right? So this, you can obviously write this as equal to also, but to emphasize the fact that this is a definition, we introduce this. So this, the reason this is true is because the way we are defining it to be true. Okay. So you take a closed curve and you integrate over the closed curve this quantity u dot ds, and ds is obviously the element of the closed curve. So if you have a situation like this, let's see. Okay, so you have a curve like this. So let's say this is my curve C, and now at a given location you have some velocity, and at this point you also have a small ds, right? So the ds is along the curve. Then we compute this particular quantity and then we see what that value is, and then that becomes my circulation. Now the relationship between vorticity and circulation about a curve enclosing a certain area, let's say A, is an interesting and important quantity. So let's say this encloses an area A whose unit normal we will write as n hat. Okay, so in that case, the first equation, this becomes integral. So I can convert now. I hope you remember the Stokes theorem. So this is a line integral, and I can convert that into an area integral, right? And for that, this will change okay. So if you just want to remember, this is by the use of Stokes theorem. Okay, so therefore, so what is this quantity? I mean, I hope you have already figured it out by this time. So this quantity is nothing but my vorticity vector. So this can be written as this, or it can be written as dA, and if you write it like this, then it's easy to see that the derivative of the circulation with respect to area, this is given as this particular value. Okay? And this simply results from the way we have defined circulation. Okay, now something to note, some important properties of circulation, and that is, one important property is circulation around any cross section. Okay, and I'll make a drawing right now. Any cross section of the same vortex tube remains constant. I hope you remember how to draw a vortex tube. We had discussed that in the last class. So we have, let's say, a closed curve, and then you draw all the vortex lines passing through this closed curve. I'll not draw that. So this will make my, so vortex tube is basically a tube made by all the vortex lines passing through a closed curve. That's what it is. So if you have a vortex tube, by the way, sorry, my other drawing is pathetic, I know. Then if you take any cross section of this, okay, okay, again, this is not that great. Okay, you take any cross section and you cut the vortex tube, then the circulation, and no matter how this is oriented, the circulation will be the same. And if you want to show that, then what we can just do to show that is recall that from vector identity, the divergence of the vorticity is equal to 0, which means that for a vortex tube, if I integrate this, okay, through that control volume, that is equal to V0. Now I can apply divergence theorem and convert the volume integral into a area integral. Right? and make this, and S here. So let's say this is the control surface, and here this volume, just a second, okay. So here this CV, this is the volume enclosed by vortex tube, and this control surface is also the surface of the vortex tube. Okay, so just one second. Okay, so sorry, there's something else that distracted me. Okay, so now going back to this equation right here, we have now converted this volume integral into this area integral, and this area integral is also equal to 0. Okay, now if you take any arbitrary cross section of this, right, then you can still break your integral over, so I think it's obvious to you why we have broken it like this. This is similar to this equation here. So this is basically giving me my circulation. So now you can create a control surface such that, on an enclosed volume, such that it is comprised of, let's say, this end, the end here, which is the bottom end. Okay, so I'll just call it bottom top. Okay, so this I will divide it into 3 parts. One is CS bottom plus same thing for top, where the top is defining for you an arbitrary cross section that you wanted to take, and then the rest of the volume of the vortex tube, and that would be CS side. Okay, and the sum of all these 3 is equal to 0, because the sum of this entire thing is 0. And all I've done is I've taken and broken the control surface, the overall control surface of the enclosed volume, into 3 different parts. Now this here, this is going to be 0 by definition, because the sides are composed of vortex lines. So there is no vorticity escaping through the sides. Okay, so this entire thing is equal to 0, which means that these two are going to be equal. So that means that CS top equal to CS bottom okay. And here you have to note that the outward pointing normal vector on this arbitrary cross section, okay, the way we have defined it, it's going to point in the opposite direction to the vorticity vector. Okay, and because of that, the minus signs are going to cancel. Okay, so this actually, because of the way we have drawn the entire system, this is now going to be equal. This essentially now means that this is true. So the circulation at the top is equal to circulation at the bottom. Okay. And essentially, again, if I had to draw this, so here your omega is, let's say, is pointing in that direction. So here also your omega is pointing outwards, and the way we have defined it, that causes this minus sign to crop up. But if you realize that it is just pointing in the opposite direction to the vorticity vector there, then you realize that the circulations are actually the same. Okay, so this fact that the circulation around any cross section of the vortex tube remains constant, this observation is also called Helmholtz law, third law or something like that. Okay, so this was an important understanding. Just a second, let me just see how much time I have left. Okay, I do have some time. So now we'll discuss another important issue related to the vorticity dynamics, and that is the vorticity transport equation. And I will tell you in advance what we are going to do. Okay, so we are going to write the Navier-Stokes equation, which in vector form will look something like this. You have the derivative of velocity on this side, and then on this side you have all the other terms, which includes the gradient of pressure, the negative of the gradient of pressure, plus the viscosity term, plus the body force term. Right? Okay. From here we are going to go to this equation, d omega by dt equal to omega dot this into u plus mu, which I'll tell you what it is. It's the kinematic viscosity and the Laplacian of not the Laplace, the Laplacian is equal to, okay, so the second derivative, the term involving the second derivative of the vorticity. Okay, and this second equation here, this is also called the vorticity transport equation for an incompressible Newtonian. This is, we'll see that this is the vorticity transport equation for an incompressible Newtonian fluid. Okay, so this is our task. We have to take this equation and we have to reduce it to this. Okay, so the way we have to do that would be, let us take the Navier-Stokes, we'll divide both sides by density. Okay, so we are going to be left with this equation, okay, minus gradient of g. Okay, and couple of important things to note here. This is also called mu, also called the kinematic viscosity. So the kinematic viscosity is the ratio of the dynamic viscosity to the density, and the body force term has now been transformed into a gradient of g. So this gradient, so basically my body force is such that is equal to the gradient of some So there was a rho here, and that rho has gotten cancelled, and so the body force basically is such that it is a gradient of some scalar g, where, for example, for if g is equal to gz, right, then fb becomes minus g into, let's say, the z vector, the unit vector in the z direction. Okay, so if basically that means that you are measuring z as you go higher up, z becomes positive and gravity is downwards. Okay, that's what this small g is. This, by the way, is a vector. Okay, so we assume that the body force is this, has this particular form, and this is going to be important. So obviously the gravitational body force does have this form, that it can be represented as a gradient of a scalar quantity, and we'll see that that has a very important role to play later. Okay, so now we have this term on the left hand side. So let us see if we can deconstruct this derivative term a little bit more. So this is the derivative, which the material derivative. So if I had to expand that, I would have to take the time derivative first and then the second term. Okay, now this second term here, this can be expanded, and this can be expanded as, and this is a vector identity, by the way. So just a second, this was u dot u, right? Yeah, and then this would be u cross So this is actually a vector identity. Okay, so this entire term here, it can be represented as this term as well, and this is equal to gradient of u dot u minus u cross, I hope you already recognize the term in the bracket, and that is the vorticity. So now if I substitute all this, into NS, and by the way, when we had written the NS equations, just a second, so we have already assumed the particular form of the Navier-Stokes for an incompressible fluid with a constant dynamic viscosity. Okay, so this is Navier-Stokes for an incompressible fluid with constant, I'm running out of space, so this is a constant mu. Okay, so the constant dynamic viscosity. Okay, so now when we take this and substitute, we should be able to get del u del t, that's the first term obviously, and then half of this gradient term u dot u minus u cross the vorticity. This comprises my left hand side. What is there on my right hand side? Well, we had already seen that this is the pressure divided by rho plus kinematic viscosity times nabla square u minus, and I have assumed this particular form of the body force. Okay, now that this equation is of this form, we have to take the curl of both sides. Okay, so what we are going to do is we are going to take both sides Okay, and we are going to take the curl, which means, let me erase this thing here and make life easier. We are going to take the curl of both sides and see what we get. Now this is where it gets interesting, because you now have to reduce each term properly. So let's take the first term of the left hand side, which is nothing by this time derivative term, and this, because it's a time derivative, I can take the time derivative inside. So this is the same thing as, so this becomes my time derivative of vorticity. Okay, and then the second term, which is cross half divergence of u dot u. This, can anybody tell me what this will be? See, this is, forget about this half. This is now this del operator cross the del operator. Now I'd told you before that if you think of the del operator as a vector, then it becomes obvious to you that this should actually be 0. Okay, so this is this is vector identity. It doesn't matter what is inside this u dot u, it will always be true. Okay, so this is something for you to check out. And then we have the third term, which is cross u cross omega. Okay, so this is a triple product, and this can be again, by using a vector identity, you can break this up into this. Minus u dot okay, this is again from a vector identity. Now this term we know is always 0, because vorticity is divergence free. We are taking not two-dimensional, incompressible flow. So this term is 0 from continuity equation, and that leaves the rest of the two terms for us. Now again, from vector identities, you can claim that rho, the del cross del p by rho, this is also 0, and this is equal to I'm sorry, not this. This is just, there is no cross product there, right? So both these terms, this term and this term, they are going to vanish. They are not going to be contributing to this equation once we take the curl. Okay, so this makes our life much easier. That leaves us, I think, so this term is taken care of. This term is 0. This term is giving us these two residual terms to deal with. Here on this side, this term is 0, this term is 0. That leaves us with this term only. So let's say what that looks like. Okay, so maybe I'll take a new page. You have del cross mu square u. Okay, so here what I can do is I can swap two operations. This allows me to swap square, because these I'm sorry, well, I'm making a mistake here. this is u. Yeah. So I've swapped these two operations, and that gives me, so this we all know what that is. This is the vorticity. Okay, so now let us put everything back and let's see what we get. Okay, so we know what the first term is, which is going to be del. Okay, and then we have another term, which there will be two terms coming from here, which is going to be okay, so there is a minus sign here, sorry, there's a minus sign here and there's another minus sign here. So these two signs are going to change, they're going to flip. Okay, so this will become plus u and the other will become minus, which was, wait a second, which is right, I think I've written it correctly. Yeah, okay, and this entire thing, so this is what remains of the left hand side. On the right hand side, you are left with a much simpler term equal to this. Okay, now I hope you've already recognized this part, right? What is this? This is equal to my material derivative or the total derivative of my vorticity. So this takes me to vorticity. So I put this, and I'll take this particular term, this one, I'll take it to the right hand side so that it becomes a positive term, plus mu times kinematic viscosity. Okay, I think we have, let's see, let me just box this, and I think we should have, so this is what we get when we simplify, and I think that's what I had said we'll come to. Okay, yes, so look, so this is what we had said we'll come to, and this is what we have found, and this is also called the vorticity transport equation for an incompressible Newtonian fluid. Also called the Helmholtz equation. Okay, great. Okay, so today I think I'll leave it here, and we will continue our discussion on Helmholtz next time and understand it a little bit more in detail. Okay, bye.